So in this section, we will discuss three major degree of logical equivalence. And I will start by saying a compound proposition that is always true. Doesn't really matter how you change the variable, it's always true. We call this a tautology. Another type of compound proposition where we have a statement that always false. Doesn't matter how you change the value on the variables, it's always false. We call this contradiction. Similar to what we did now in the exercise, where we have P or Q or R. And this is impossible to be exist or true at the same time. And this is what we mean by contradiction. The third type, which is basically a compound proposition that is neither a tautology, it's not always true, and it's not always false, it's not always contradiction. We call it contingency. And contingency is basically any propositional variable. P as a statement, it has the value true and it has the value as false. So it's possible to have it true and false values. It won't be able to have a one single statement that it's always a tautology, it's always true. And that's why we call it a contingency. Let me give you more detailed example. So in this truth table, look to that truth table and look to P or not P. Now if you look to the value of P or not P, they always true, because if P is true, not P is going to be what? False. Now true or false is always true. Again, if P is false, not false is true. It's false or true is always true. So P or not P is a tautology. It's always true. Doesn't matter what the values of P or not P are. So it is always a tautology. Now look to the second one, which is P and not P. Now with the AND operator there, you will find that this is a contradiction because it's always false. You cannot have P and not P at the same time. And the outcome of this statement always false. And you will find that true and not P, which is basically false. True and false is always false. False and true is always false. Now contingency is a best example of contingency in this truth table is the propositional value P. The variable P is contingency because it has T, it has true values, it has false values. It's impossible to have a proposition where it's always true or it's always false. You can see here in the first row we have true, and the second row we have false value. Now this leads us to the second definition, what we mean by equivalent. So the compound proposition P and Q are called logically equivalent if and only if P implies Q and Q implies P. And it is a tautology. And that notion, which is an equal sign with another symbol of sign, it's P equivalent to Q. It's not equal sign as you use in calculus. It's an equivalent sign. So this means that the truth value of P and Q are logically equivalent, are the same. Let me now give you some example of that. Imagine we have a compound proposition P and Q, and they are logically equivalent if P and if and only if P if and only if Q. And this is a tautology. We write this statement as P if and only if Q, or P is equivalent to Q. So how we can study this? By taking the truth table. The two compounded proposition P and Q are equivalent if and only if the columns in the truth table they match in their values. So to do this, we make a table of the truth table to represent that. So let us take the P value first. You start always by saying true, true, false, false in the first column. That's a default. You fill this. For Q, now you need to flip them. True, false, true, false. Similar to what you did in before. Now the value I'm looking for is not P or Q. So I have to find out the value of not P. This is going to be the third column. Now let me make that result. Not P or Q, you will find that it's true for the first row, it's false for the second row, and it's true for the third one, and it's true for the last row in the table. Now the next step, I want to find out the value of P, then a Q. Now to do so, I have to refer back to the truth table of P, then a Q. And you see here. Now, this is the value of P, this is the value of Q. I need just to implement it in the rule. Now, P implies a Q. I have P, true, and a Q is a true. Now, back to the truth table of conditional statement. True, then a true is a true. So I will put T here. Once I use the truth table, it's clear for me which values I have to put in this table. True, then false is basically false. False, then a true is a true. False, then false is a true. Now look to the columns where we have not P or Q, P, then a Q. You will find that their truth table values match. So, both statements now we can conclude they are logically equivalent by studying the values in the truth table. So, as long as the values are matched between the two compound statements, we now simply could say that not P or Q is logically equivalent to P, then a Q. And this leads us to a famous logical law called De Morgan's law. Now, not P and Q, this is equivalent to another statement, and you can make the truth table of this to verify. Now, once you have the not outside the parentheses, once you want to include it in and remove the parentheses, you need to flip the sign in the middle. So this could be converted to not P or not a Q. This is what we call the first De Morgan law. Those laws, now don't worry, you don't need to remember them. They will be provided in the exam paper. You will find a table of those laws in the exam paper so you can use them. The second De Morgan law, it's basically saying not P or Q. Now we want to remove the parentheses and we want to put the negation inside the parentheses, so it will be not P, and we flip the or to and this will be not P and not EQ. And this is what we call the second De Morgan's law. Now let me do the truth table for the second De Morgan's law so we understand where it comes from. Again, we start with the first column. We put the first variable, which is P. We put the variable's value, true, true, false, false. For Q, we put a true, false, true, false. Now, the first one I want to do is not, and the second one is not a P and not a Q. I want just to find out the negation of P and negation of Q. Now, let us put the first term, which is P or Q. Let us find P or Q, and we want to find the not of this column, which is not P or Q. So not true is false, not true is false, not true is false, and not false is true. Now let us find the last value, the one I want, the one I'm looking for, which is not P and not a Q. Now look to the values of not P and not a Q and just do AND operator between them. False and false is? False and true is false. True and false is false. True and true is true. Now, look to that truth table and look to the last columns. You will find that the truth value for both columns, they do match. So we can simply say now that, based on the truth table here, we can conclude that not P or Q is logically equivalent to not P and not a Q. You will find there is so many key logical laws that you can use here. As I said, they are going to be provided, and I have put an image in the Google Classroom page with a table of all of them. So you can use it in the coming activity, and you can use it in the coming assignments and exercises. There is, for example, what they called identity laws. And this law is really simple. It says any propositional statement mixed with a true value. Big T is a tautology. So any truth value, any propositional statement with and operator with a tautology leads us with a logically equivalent statement with P. So the propositional statement will maintain its identity. And this is when you multiply any number by 1 in calculus. When you multiply any number by 1, the result is going to be the same number. X multiplied by 1 is X. So identity law say P and a tautology is P. P or a contradiction is always P. When you mix with or a connector or gate, P with a contradiction, with a big false value, it always gives you the same original propositional statement P. Now with domination law, here we are saying the other way. If you make an or statement between P and a tautology, the tautology will be the one who dominates the truth table. So the outcome of this is always true. When you mix a proposition statement with a tautology, with OR gate, the outcome of this gate will be always true. It will be always a tautology. Now when you mix P with AND gate, with a contradiction all the way, the outcome of this mix will be always a contradiction. Because AND gate or the AND operator needs to have two true value in order to be the outcome to be true. There is another laws you can find. For example, P or P is P. You just basically end up with the starting point. With any statement or that statement is always the original statement. P and P is also P. The outcome is always P. The double negation law, not P, is P. Inverse of the inverse is the original value. If P is true, not true is false, not false is true. So it will lead you to the first starting point. And also there is another negation law, which is P or not P equals or equivalent to true, to a tautology, because you are basically mixing the value with its inverse, and this leaves you with a tautology. Once you have a statement, and you do AND with this statement with its negative or its inverse, you end up with contradiction. You will find that there is a list of other laws, like the commutative law, where we say P or Q is similar to Q or P. You just flip them. P and Q is similar to Q and P. The associative law, let's say you have X multiply or X multiply parentheses 2 plus 1, and you want to include the multiplication in the parentheses. This is the same. This is the same law that we use in logic. Now I want to take the parentheses out. I can just simply say P and Q and R could be rewritten as P and I put parentheses between Q and R. The distributive law. Now, if we have a logical statement where we have a parenthesis P, or, and then we have nested parentheses between Q and R, we can distribute the first or in the middle of that equation. So we will take, for example, P or Q, and this will be and P or R. That's it, guys. Now when we have P and Q or R, we can just distribute the and between them, and we will say P and Q or P and R. And we can use those laws as they are mentioned here. You don't need to worry about them. The observation law, P or P and Q, is it basically equivalent to P. You don't need to worry about it. P and P or Q is also equivalent to the value P. So these tables are giving you logical equivalent involving conditional statement as well, and there is logical equivalence involving biconditional statements, which can be useful to do more proof that two statements are logically equivalent or not. We will take more example about this, and we will study each step we use and employ those laws. How we can employ them to prove or disprove that there is two statements logically equivalent. So once we have the ability to compound two or more propositional statements, and we have laws to support us to employ those laws in our proof or disproof, we can basically construct a new expression and a new logical expression. And we can show that two expressions are logically equivalent by building a series of logically equivalent statements. For example, to prove that A is equivalent to B, we produce a series of statements. Let's say A is equivalent to A1, and then we use the law to simplify the proof further until we can conclude that AN is basically equivalent to B. Now let us take an example. So in this example, we have two statements. The first statement is basically not parenthesis B or not B and Q. We want to show it's logically equivalent to not B or not Q. So let me just explain how we start with this. So the first step, once I see the statement, I just recall the second De Morgan law. And this law is telling me, if I take the parentheses out, the first parenthesis out, if I just simplify it to simple form, I need to take this parenthesis out. So the Morgan law says, once you have a negation outside the parenthesis, and you want to take the parenthesis out, you just need to flip the middle sign, the middle operator. So this equivalent to not be, now I put the not inside, now I change the or to and this second parenthesis, the nested parenthesis, will take a negation. So this will be not be, and Q. So I use in the first simplification De Morgan law. So the second De Morgan law helped me to simplify and to come up with this statement. Now look to the second statement and look to this portion of this statement specifically. The right hand side of the and. If you look back to the first De Morgan law, we say if there is a not outside a parenthesis where and involved in the middle, we can remove the parenthesis, but we need to change and to or, right? So not be, now the and becomes or, not Q. So I put the negation inside the parenthesis. This is all I did. Now, can I simplify this? Not be, I could use double negation law, which is basically not be is equivalent to B. So I will delete not be and make my life easier and make this look like B. Now, I am here where I have not B and a parenthesis P or not Q. Now let me distribute the and operator between those three propositional statements. what I will do not P and P, okay? Now take the or here to the middle, not P and not Q. Now can I simplify this? Not P and P by another law. We can just simply we can simply say by the distribution law, because not P and P is always a contradiction. We can replace it with false. So we will put big F here. We leave the or operator, and we will have something in the middle. Those are not touched. Now, by commutative law, which is basically saying P or Q is equivalent to Q or P, we now need to flip them. So we will flip those, so it makes my life much easier to simplify it. And then I can say not P or not Q or F can be simplified to P based on the identity law. I say any statement with or operator with a contradiction leads me to the original statement. Look to this law, the identity law. P or F is logically equivalent to P. So I end up with not P and not Q. The reason why I take the F back, because basically anything with F is leaving me to the, based on the identity law, lead me to the original statement. Now the last step is just to prove to us that this statement is logically equivalent to the original statement that we start with. So let us take another example. We want to show that P and Q, then Q or P or Q is a tautology. So the outcome of our simplification of the original statement should lead us to big T, to a tautology. So take the first statement, the original one. Take the truth table of if then, the conditional statement. I can just introduce the negation here, where I have not P and Q, and I convert the then statement or the conditional statement to or, where P or Q. Now refer back to the truth table of the if then statement if you are not clear why the first statement is look like this. Now the first De Morgan law is telling me if you have negation outside parentheses, you can put the negation inside the parentheses and you need to flip the middle operator, where we have not P or not Q. And this basically leaves me to use the associative law, where I can flip them, not P or P, or not Q or Q. Now we understand by the truth table that we just did in the previous example that not P or P is always leave us to true. By the first law we just did. I could refer to it here. So P or P or T is always true. Guys, this is what we did, right? So in here, I'm saying P or not P or P is always true, or not Q or Q is always true. True or true is always true. So the original statement is a tautology. Now you will find this really, really hard to understand if you don't practice it. Now you will find those laws, the table of laws in Google Classroom as an image, and now we need to work in a group of two to solve the following activity. So the first one, not P then Q, is equivalent to P and not Q, which are logically equivalent. And the solution for that, you can simplify not P then Q to not parentheses, not Q or P or Q. And the example we did earlier, and this is the truth table for it. This is the example we just did in the previous slides. Okay? Now, look to this example. What we start with was P, Q, and then we find not P, and then we find the OR of not P and Q, and then we prove that not P or Q is equivalent to P implies Q. So this is the example I was asking you to refer to. Now, we're using the second De Morgan law. Now we want to break the walls. The walls here are the parentheses. So every time you see parentheses, give them high priority. You need to get rid of them first. And now, once we put the negation inside the parentheses, we have not B, and the AND will, the OR become an and not a Q. Now, not B is what? Is P. So this is basically not P is using the double negation law, P and not a Q. So we have started with something and we end up with not P and not a Q, which is logically equivalent to the starting point, which is not P then a Q. So that's the first example. Now the second one, we want to show that P and Q, then Q or P or Q is a tautology. Again, by the example earlier, once we have then, we can convert it to what? To this, to P implies a Q. We can convert it to not Q or not P or Q. So now give the first one not, the first, the premise, not, and then change the arrow to our operator. You will end up with not P and Q or P or a Q. Now by the first De Morgan law, we want to get rid from the parentheses, so we will put the not inside. So it's going to be not P, and the AND will become OR, not a Q. Now keep the OR, keep the second part of the equation as it is. We have not done anything with it. Now with the associative law, it's clearly saying here, not P or not a Q or a Q could be converted to not P or P is always what? True. Or not a Q or a Q is always what? A true. True or true is a true, so this is a tautology. Who got the same?